Hey, chemistry. So, different setup today because um, the lab requires a visual. So, here is our visual, right? Usually I'd be up in the top corner, but today we got a visual of these little model pieces. There are sticks and springs and little black and yellow pieces, and what they are, what they represent, are organic atoms. They're carbon and hydrogen. They're hydrocarbon atoms. The Organic Models Lab, which is what I'm doing here, is on pages 31 and 32. Now, again, it looks a little funny on here. I don't know why it's all wackadoodle here, but it's fine, right? We're still gonna do 6 compounds. We're still gonna do 6 drawings based on the compounds. We're just gonna change what the compounds are. You don't need to worry about the teacher's initials. Normally I would go around and just like, okay, this is going to be practice of the naming instead of, okay, this is how we're going to talk about naming, right? So I'm going to empty out the model kit here because I also need, oh, runners. Okay, running all over the place. My desk is uneven. I get it. But I also need my desk a little bit because, let's leave that off to the side. I need to make some changes and write some stuff. So you guys can actually see the little corner just here of my drawing pad. This is what I've been writing all your notes with. So I have a pen, and what I can do is write on this. Right, so we are going to do methane, we are going to do ethane, we're going to do propene. We're not going to do this. I'm gonna cross this out. We're not going to do 2-methylbutane. We're going to do 2-butene, and I'll explain what this number means. I'm not going to do that. We're just going to cross that out, and we're going to do this. We're going to do 2-pentyne, and then we're not going to do this either. What we're going to do is actually 3-heptyne. All right. So we're going to do those things, and additionally, I hope that somewhere I was smart enough. Yes, I was. Here they are. Okay, so you'll need your reference table as well. On page 7, here we have organic prefixes. Now, off the top of my head, I'm pretty familiar with them, but I wager that you are not. So, as we do these, you will need your reference table to kind of look at things. I am so sorry. I thought that was on mute. There we go. So much better. Sorry about that. One take, kids. One take. Now, here's what we need to do. I'm going to talk a little bit about this naming concept because we've talked about this before. The ANE, the ending, tells us what kind of bonds we see, right? So these sticks represent single bonds, and I can put them in between 2 carbons and say, okay, look, there's a single bond between the carbons. And if you remember, the ENE means a double bond. Now, I very much cannot take this stick and attach it to this carbon, and then take another stick and somehow attach them. That's just not going to work, right? What I can do is there are springs in my little model kit here. There should be some more springs somewhere. There they are. I'm trying to move stuff without flying all over my desk. So what the springs can do is they can bend. And when they bend, they make a double bond, right? If I needed a third, then I could take a third spring, attach it, and bend it, and make a third bond. Right, so that would be a triple bond. And when we get to it, and we have to get to it, we'll get to it. But I'm going to start with the first one, methane. Right? Ane, A-N-E, means all single bonds, means I only need sticks. And that meth prefix, yes, meth, like the drug. I'll get into that in a minute. Not making drugs, but what the meth there means. But if you look at your reference table, right, on page 7, on table, I don't know what table it is. It might be table P. It's table P. So the organic prefix as meth means it's 1 carbon. So I need to take 1 carbon, right, and knowing that this is a hydrocarbon, I take 1 carbon. There's my 1 carbon, and I need to attach all single bonds. And I don't need to attach any other carbons, but on the end of each single bond, I need a hydrogen. Boom. And And there is methane, and it occurs to me that I may be too zoomed in. So let's see if I can change that a tiny bit. Yeah, that's fine. Alright, we'll figure it out. But here's methane, right? 1 carbon with 4 hydrogens. And this is actually like a 3D model. This is a representation of what would it actually look like. There we go. I don't know which way to go. Hard for me to tell on the camera. Now, on the actual lab, there's a structural drawing that we have to do. So that structural drawing that we have to do for methane is 1 carbon. It's a single carbon with 4 hydrogens attached to it. All right, that's what it would look like. Now, sometimes it's easier to use the model to make the drawing. Sometimes it'll be easier to make the drawing and then fit the model to it. Ethane, if you look at table P, you'll find that ethane means 2 carbons, ane means a single bond, and because it's all single bonds, everything else is going to be hydrogens attached. So if I use the picture to make this, then this has to go away. It should actually be another carbon, and I should single bond everything else to be hydrogens. 1, 2, 3. That's a runner. That's fine. Model kits are a little dated, but that was so loud. I'm so sorry. RIP headphone users. 1, 2, 3. There. That's ethane. Right. So 2 carbons, single bonded. Let me move some of these out of the way. I'm just trying to figure out where to put them. I guess I'm just this way. Runner. That's fine. But everybody just get out the way here. And I'll make this clear. That way it doesn't look so cluttered. Because it looks awful cluttered there. I hadn't looked at it until just now. Really. Not a lot of pre-testing that happens here. Alright. So, there's ethane, right? Carbon, single bonded to another carbon, and then hydrogens fill in the gaps. Alright? That's 2 easy ones, right? Propene. No, prop. P-R-O-P. Means 3 carbons are chained together. Okay. So let me just take my hydrogens off. I'll leave the hydrogens off to the side here, because I'll probably need a bunch of those anyway. Alright, so I need 3 carbons all attached to each other. And normally, that would kind of look like this. But, if you look, it has an ENE ending, which means one of these needs to be a double bond. And again, since I can't use the stick, I have to use the springs. And what the springs are going to do, they are going to allow me to make a double bond. Oops, so loud, so sorry. Double bond between the carbons. Right? So here are 3 carbons, prop, with a double bond for the ene. Right? I could put it this way, I could put it this way. It kind of doesn't matter where I put that double bond because it's the same molecule. The number is going to tell us something in a second. The other thing that I need to do is fill in all the rest of the gaps with hydrogens. And when I do that, I get something that kind of looks like, I'm just trying to figure out how to arrange that, like this. Right. So the way that I have it out there, and I'll try to draw it the same way that we have it, I have a carbon, single bonded to another carbon, double bonded to a carbon. The last carbon looks like it has 2 hydrogens. The middle, sorry, I'm trying to draw without looking. The middle one only has 1. This one on the end here has 3. Right? And you'll notice every carbon still has 4 bonds attached to it, right? If I look at this carbon, I have 1, 2, 3, 4. Every carbon wants 4 bonding, or 4 bonds on it. This is considered unsaturated because it's not filled, right? These 2 carbons are being kind of selfish. They don't need to be double bonded to each other. There could be other stuff here, but they choose to double bond. Right? Now, the next one gets a little more complicated because it has a number, and the number tells us something specific. The number will always show up, will only show up with something with a multiple bond, so something with a double or a triple bond. 2 butene means that I have a double bond, right? The ENE ending tells me I have a double bond, and that but tells me that there are 4 carbons, right? The 2, what that 2 actually tells me is that I should go 2 carbons from the end, then put down my double bond, and then put the rest of my carbons. So I have 1, 2, here's my double bond, I need a total of 4 carbons, so there it is. This is 2 butene, it just needs some hydrogens to fill in the gaps. That totally came out, but it's fine. I'm so sorry if all of this moving and scratching is crazy loud. Did not really anticipate that when I was thinking this through. Hello? Reattach there. There we go. So here's the model for 2 butene. I have a carbon, carbon, there's a double bond, another carbon, everything else is hydrogen. So if I'm drawing this out, I would see a carbon single bonded to a carbon, double bonded to a carbon, single bonded to a carbon, and then each of these is a hydrogen. And again, notice every carbon has 4 bonds on it. They may not be connected to different things, right? These two are double bonded to each other, but there are 4 bonds. All right, now things are getting a little more complicated. 2 pentyne, right? Pentyne, YNE, means a triple bond. So I need to find my last spring. Because it's another 2, again, sorry for the loudness. Because it's another 2, I know that I can keep at least one of these ends the same, so I'm going to keep this end the same. This YNE means I need a triple bond. So there's my triple. And pent means I need a 5th hydrogen. Or, sorry, a 5th carbon, so I'm going to put it over here. And then I'm going to fill in the gaps with hydrogens as necessary. Right? And there, that, let's turn it a bit, that is 2 pentyne. It's 2 because I go 1, 2 from the end. Here's my triple bond. Then I finish out the rest of my carbons. 3, 4, 5. Everywhere where there was an open space to attach something, I attached a hydrogen. So, if I'm looking at it, and I have to draw it, I have... Ooh, oh goodness, what was that about? Hello? Don't do that. Please don't do that. I want to draw on this. Thank you. Alright, so 2 pentyne means 1, 2 carbons, then my triple bond. Carbon, carbon, carbon. This has 3 H's on it. This has 2 H's on it. This has 3 H's on it. I want you to notice, like, physically what happens here, right? These carbons attach at a bend, and then because of this triple bond, it has to be like a straight line. So it makes a straight line where that triple bond is. Physically, that's actually what happens. Double and triple bonds will tend to straighten out the molecule. Otherwise, it would be this kind of weird zigzag chain. Right? Now we got one more. 3 heptyne. All right, 3 means I go 1, 2, 3 from the end. Then I have my triple bond. And hept means 7. So I actually need 2 more carbons. And I'm going to be a little clever. I'm going to attach them to this side. Because that means I need to do the least moving of other molecule pieces. Then I need to attach a whole bunch of hydrogens. And boy, did I pick the wrong kit to use, because this one has large bonds. Some of the other kits have smaller wooden dowels for the bonds, so it would have been easier to see on camera. That's not a big deal. We'll get there. Okay. This has to attach here. Alright, so I need to zoom out a little more. Alright, yeah. This is 3 heptine, because I go 1, 2, 3. Here's my triple bond. 4, 5, 6, 7. Right, and everywhere else where I could, I'm attaching a hydrogen. Now, somebody might be like, well, what about, why wouldn't I count 1, 2, 3, 4, and then triple bond? Well, why would I count all the way to 4 if I can count to 3? You always count as few as possible when we're given the nomenclature, which is the naming scheme. When we do naming for organic stuff, we want to count as few things as possible, partially because there's a lot of counting that would have to happen otherwise, and partially just for consistency. You always count the shortest end to the multiple bond. So this is 1, 2, 3, there's my multiple bond. 1, 2, 3, 4, well, why would I count to 4 if I can count to 3? And again, if I were drawing this out, I would see, what would I see? Oh boy. Can we, oh, there it is. All right, good. Lost my pen for a second there. So I would see 1, 2, 3, triple bond. 1, 2, 3, 4, and attached to, oh goodness. Sorry, I'm just like running into the molecule here. Attached to each of these, nothing on those because they have 4. Each of those is a hydrogen. So we have hydrogens all across the board. Right? And that's what we have. That's how that kind of goes. Right? The model kit helps you to visualize, it helps us see. And again, right, there's these bend. There's a bend here, and then all of a sudden it has to go straight because of the triple bond. There's a bend on this side. I'm going to use, actually I'll probably use this model, because it's already right here, to demonstrate something else, but really quickly, while I have the lab here, excuse me, goodness, why don't I finish out this conclusion? No questions here, because there's not a lot of nomenclature that you really have to know. This is really just scratching the surface of organic chemistry, scratching the surface of these naming concepts. I'm going to shift this over a little bit so I can actually draw my pen. Alright, so in conclusion, right, our conclusion here, just to state some stuff, again, things to remember, things to keep track of. All saturated hydrocarbons have only single bonds between carbons. The general formula, let's not worry about the general formula, because honestly that's a little too mathy for me. Each member of the alkanes being all single bonds, differs from the one before it by a single carbon unit. So heptine is different from hexine. Like hexine wouldn't have this carbon down here. That wouldn't be present. So that would just be a hydrogen. But oops, sorry. Again, really loud. Apologize. Rip headphone users. It would be hex because it would only be 6. All right. All alkanes belong to the same homologous series or family, right, of hydrocarbons. They all have only single bonds. So this is not an alkane because it has this triple bond. This hydrocarbon is actually unsaturated. It can be either alkenes or alkynes. And they're considered unsaturated because of the multiple bonds they contain. When I talk about a multiple bond, what I mean is a triple bond or a double bond. I consider that a multiple bond. Right? Now, this is something that you haven't seen yet. Alkenes and alkynes undergo addition reactions. There's more on this on the next page, while alkanes undergo substitution reactions. And if you see here, right, again, oh geez, I'm just going to put that away. This right here, right, is the alkyne. This is the unsaturated portion of the alkyne. This is unsaturated because if I remove this bond, right, what, I don't know if you can see, oh, you can, oh, yep, there it goes. There are bonding sites, right, so these holes represent bonding sites, and that's where something could be added, right, so if I remove that multiple bond, I could add something new, and that's why unsaturated hydrocarbons can undergo addition reactions, because you can add things to them. If I go all the way back up to ethane, I'm going to try to be like gentler with this because I know it's very loud. If I go back to ethane, if I go back to this molecule, right, there are no open spaces. There's nowhere to put anything. So I would literally have to substitute something. I would have to take something off and then replace it. I wouldn't be able to add anything to it. Right. Now, this lab is online. Right? There should be an assignment for it. I just want to show you something visually that we already covered in the notes. My fully remote students, you have already completed these notes, so you've already seen this, but I just want to show you visually isomers, right? So these are substances with the same chemical formula, but different structures, right? And the simplest one to show is probably butene. Yeah. So what I'm going to do, I'm going to make a skeleton. I'm going to get rid of all the hydrogen, the actual pieces. I'm just going to have the little sticks pointing out. And the sticks will represent hydrogens, and that's fine. Alright, so, isomers, and let's, like I said, use 1, 2, 3, 4, oh gosh, so that, again, sorry, I know things are very loud, I apologize. New setup, I feel like it was bound to happen eventually. Alright, let's get rid of those, alright. So again, just imagine that there are the yellow model kit pieces. They are attached to all the ends of the sticks here. Okay, or you can all disappear too. That's fine. So this is a form of butene, right? 1, 2, 3, 4, and there's a double bond. So 4 means but, double bond means ene. This is 1 butene because I go 1 carbon and then I see my double bond. I can change this into 2 butene, which is the one that we had, if I move this carbon over. And now it's 2 butene because I go 1, 2, there's that. Those are isomers of each other. Technically, they're the same thing, right? It's 4 carbons, and then however many hydrogens are out here. It's 10. Might be 10. No, it'll be 8. 1, 2, 3, 4, 5, 6. Yeah, it's 8. So that would be the same thing. But structurally, this structure and this structure act wildly differently. They do wildly different things. In fact, not even just that. This structure and this structure do wildly different things because of their shape. And this is like, again, this is a very dramatic example, but the difference between this structure and this structure doesn't look like a ton. Here they're both going the same way, right? Both my little branches are going the same way. Here, my branches are kind of going opposite ways. But because of that change, it will change how other molecules react with it. It will change how it interacts with other things. It might change how your body interacts with it. This, and I use this in class, this is one of the minor differences that exist between something like cough medicine or methamphetamine. These are wildly different drugs that have wildly different effects on the human body, and it's a super small change in the molecular structure. Super small change. Makes a huge difference, right? These isomers, this is the reason that drug testing and the manufacturing of pharmaceuticals is such a big deal. This is why organic chemistry, in and of itself, is like its own class. And it's why so many people dislike it, because like differences like this are basically game-changing. And it's just odd. It's strange that has so much of an effect. A little structural difference. Doing that can make a ton of difference. But anyway, the lab is all set. We've finished all the notes. There should be a posted link or a posted PDF online that is basically the final study guide, and we'll be going over that in various ways over the next few days. I would encourage you to take a look at it. It's a modified version of a Regents review sheet, or a Regents review PDF, because this class usually is, getting ready, prepping for the Regents. Ooh, okay, screensaver, good times, got me monologuing. But since we skipped a few things and we don't have the Regents, I can still use most of it, right? There's no reason to reinvent the wheel. So I can still use most of it to review for our final. Again, as a reminder, if you haven't seen it, if you haven't checked my CBA, our final is multiple choice. I say our final. Y'all's final is multiple choice. 85 multiple choice questions. 70 of them will count, which basically means you get 15 freebies. That doesn't mean only answer 70 questions. That means answer every question. And as well as you can do, that is how well you can do. Or that's how well you will do, right? Answer every question to give yourself the best opportunity to get as many points as possible. But I'm basically giving you 15 freebies. So enjoy, right? Don't make me regret that. Please study. It is the first test. Yeah, I think that's it. Let me know if y'all have questions, and next time I see you will be in either a review video or at the final. Take care, kids.